Welcome to Homework Lib.
Hi, so over here we're going to generate the molecular orbitals of of different molecules in order to know what is going to be their total spin. So we're going to start with O2. The diagram corresponds to the valence electrons, 2s and 2p electrons of oxygen. We're going to put them on both sides. They are going to be at the same energies because they are the same oxygen atom. And the resulting molecular orbitals are going to be the sigma and sigma star 2s orbitals. Here we need to add the total number of electrons of each of the oxygen atoms. So we know that oxygen is going to have a total of one is going to have a total of 3, 4, 5, 6 valence electrons each of them. So the ones on the 2s orbitals are going to be employed to fill out the 2s orbitals that we have here. Following that, we're going to have the pi orbitals coming from the pi interactions between p orbitals. Remember that pi interactions are the ones that look like this, and that sigma interactions, whenever we're dealing with p orbitals, are going to look like this. And in the case that we have s orbitals, are going to look like this. So both of them are sigma, and the ones here are going to correspond to pi. So this is just part of the nomenclature, but for solving the problem, let's just go ahead and continue with the molecular orbital. So we're going to have the pi orbitals that are going to be lower in energy. And next we're going to have the sigma orbital over here. We're going to follow up with the pi star and sigma star orbitals. Remember that whenever you write down an orbital, you need to add the same one with a star added to it, which needs to be in a higher energy. That is usually known as the antibonding orbital. So what we get here is that when we fill out with the number of electrons that oxygen has, we're going to find that we're going to get two electrons that are going to be unpaired. So two unpaired electrons corresponds to a spin equal to 1. So oxygen is going to have a spin, a total spin equal to 1. Now let's go ahead with NO. And as you will see, the orbitals are going to be quite similar, but the only difference is the number of electrons that the nitrogen is going to be able to give. So I'm going to write down the nitrogen over here. That is going to have the 2s and the 2p orbitals. And we're going to get only 5 electrons on the left-hand side. Here I'm going to squeeze a little bit the orbitals. Let me put down a little bit lower in energy the orbitals from oxygen, since they are going to have a lower energy. So we have the 2s and the 2p orbitals over here. And after we generate the molecular orbital, what you're going to see is that we're still going to have the sigma and sigma star 2s orbitals that are going to be filled. Next up, we're going to get the pi orbitals, a sigma orbital, the pi star orbitals, and the sigma orbital over here. Why do we have a difference between this diagram and the one on the top? That is going to be because of the number of electrons that we need to add. So when we are done adding electrons, you're going to see that we're only going to have one electron that is going to be unpaired. So for NO, the total spin is going to be equal to 1/2. Let's follow it up with HF. HF is going to have a single 1s electron coming from the hydrogen, and in the case of the fluorine atom, we're going to get the 2s and 2p, the 7 electrons corresponding to its valence. 1, 2, 3, 4, 5, 6, and 7. And now what is going to happen is that since we only have one s orbital, that one s orbital can only interact either with one s orbital of the fluorine or with one of the two p orbitals that are going to be present. So essentially what is going to happen is that we're going to get two p orbitals that are not going to interact, so they're going to have a slightly higher but essentially almost the same energy that they had originally. We're going to have one sigma orbital coming from the interaction of one s orbital and one of the two p orbitals. So it would look like this. And finally, we're going to get a pair of orbitals over here coming from the interaction of 1s and 2s. And after we have done that, we're also going to have the corresponding counterparts that are going to be the p. These are going to be pi orbitals, and here we're going to have the pi star and sigma star orbitals. And these are the sigma and sigma star coming from the 2s orbitals. So let's fill them out. We have a total of 8 electrons over here. So 1, 2, 3, 4, 5, 6. Sorry, here a little mistake. This 2s orbital would be a lot higher in energy because here it only counts the interaction of the fluorine atom. So disregard that one. Perfect. So with this, HF is going to be a total spin equal to 0. So now for CO and CN, we're going to have very similar molecular orbitals. The only difference is going to be the number of electrons that we need to add. So let's go ahead with the carbon atom. We have the 2p and the 2s orbital, and we only have 4 valence electrons. And for the oxygen, we're going to have 2s and 2p orbitals as well, but now we have a total number of 6 electrons. So even here I'm drawing them at almost the same distance, but the orbitals from the oxygen atom are going to be lower in energy. So the diagram is going to look like this. We're going to have the sigma and sigma star coming from the 2s orbitals that are going to interact with each other. Those are going to be filled completely. And next we're going to get the pi orbitals coming here and the sigma orbital. We can go ahead and write down the pi star and sigma star orbitals. And the number of electrons that we need to add here are going to be 1, 2, 3, 4, 5, 6. So we get 1, 2, 3, 4, 5, and 6. So the total spin for CO is going to be equal to 0. Now, what would happen if instead of having an oxygen atom, we had a nitrogen atom? So in that case, the only thing that would change would be that over here, I would need to get rid of one of the electrons. So that means that my diagram, the only thing that is going to change is that I'm going to have one electron less. So in CN, we're going to have one ampere electron, so the total spin is going to be equal to 1/2. That's why Cn minus is going to be more stable because it's going to be completely filled, and Cn minus is usually going to have 0 as total spin, right? And the final one that we need to do is CH4, which is going to have also 0 ampere electrons. And here, since I don't have enough space, I'm just going to get rid of these diagrams. And we're going to take advantage that we already have a carbon atom over here. So over here in molecular orbital theory, what is going to happen is that we will draw the orbitals for the 4 hydrogen atoms. So these are all 1s orbitals coming for 4 hydrogen atoms. And the interactions are going to be the following. We're going to have the interaction of a 2s orbital that can interact with one of the 1s orbitals over here. We're going to have the interaction of 2p orbitals with these 3 hydrogen atom orbitals. That is going to generate these 3 mixed orbitals that we're going to get that are usually called the hybridized orbitals. Next, we're going to get the sigma star over here that is not usually labeled as sigma. It's just like a different wave function. And we have the antibonding corresponding to the three orbitals over here. Notice that in CH4, all of the interactions are going to be sigma because the mixed orbitals are going to be looking towards the bond directions. So now we just need to fill up the total numbers that we have. In this case, we have a total number of 8 electrons to fill, so that corresponds to 4 completely filled orbitals, and that's how we get the value for zero. So with that, it would be all. Thank you very much and have a good one.